And the next presentation we have is by Guren from Alibaba about a way to atomically attach or atomically issue I/O to external accelerators for mainly data center use cases. So with that, over to you, so I don't have to talk so much.
Thank you, Philip, for the introduction. Hello, everyone. My name is Guren. I'm from Alibaba Damo Academic. So my presentation out. Yeah. Wait a moment. But this is correct. What's the problem? Yeah. Wait a moment. Oh, okay. Let's start. Hello, everyone. My name is Guren. I'm from Alibaba Damo Academic, Xuantie Processor Team. Today, I want to talk about the RISC-V heterogeneous programming paradigm. The presentation contents have three parts. First, motivation. We talk about the traits and the problems. And the second is the solution with two proposals, AIOE and the GIPC. The last is final remarking. So, motivation. Here we go. With the AI era arrived, and the requirements of the high-dimensional tensor computing workloads are increased. So the general-purpose processors cannot afford this kind of workload, and we need to offload them to the domain-specific architecture, such as the TPU, NPU. And on the other hand, the requirements of the data, the high throughput and low latency data processing workloads are also increased. So we need to offload them to the data processing unit, such as the ISP, DSP, and the codec, NVMe, compression, decompression, some about the memory movement, some about the I/O input output. So from the internal SoC chip to the advanced packaging chiplets or to the both connected systems such as PCIe, CXL, the modern computing systems have become natively heterogeneous. That's the reality of the world, and it's the truth. In this room, most people are focusing on the ISA design, but who cares about the convenience of the heterogeneous programming? Yeah, so let's have a talk about the traditional heterogeneous program. This book I bought over 20 years ago. It's a very old book, and it just happened maybe yesterday for me. So time is passed so fast. And with the decade years development, the Linux have become the most complex and the biggest monolithic Linux kernel of the world. The most attract me of the Linux is that this kernel supports tons of the device drivers and the components, and that is easily make the Linux running on any hardware. You just throw the Linux on any hardware, it's running, it's incredible. And we would find the problem is this kernel have very deep kernel programming stack. And if the user space want to access the device, it need to cross this kernel. And the problem is obvious that the privilege context switch overhead cost, and second, the synchronization primitive overhead about the submission the jobs to the device. And it's very weak for the isolation if the device hardware is not properly designed for the safety or the security. But the most important thing I think is development is very complex and expensive, because if you want to migrate the Linux driver to other operation system, it's very hard work and it's a very cost investment. So some industry cases come out that they bypass the Linux kernel, such as the SPDK, DBTK, this kind of the software infrastructure with some of the hardware features, such as the RDMA, IOMU. But the problem still remains that the synchronizing primitives overhead is still there. Its immediate is not enough. And the second is the device cannot be shared across process and virtual machines. Here, the device, I means the basic element instance of the device. Okay, so what is an ideal heterogeneous programming paradigm? Okay. Here is our solution with two proposals, AIOE and GIPC. AIOE means the atomic I/O Enqueue. Its extension for the ISA specification is just involve some instructions and CSRs. And the GIPC means G-state table in process context for the RISC-V I/O memory specification. It's a non-ISA specification, and it's solve the AIOE usage and the virtualization scenario. Okay? So let's get more detail of them. First, AIOE. We introduce one unprivileged instruction such as the uEnqueue instruction, 64 bytes. Atomic I/O store, yeah, and it was a single write 64 byte to the target address with the status result. The source operand is come from the 8 consequent general purpose registers, and the destination is the target address. The target address is the AIOE PMA. We introduce a new PMA, and this is for the security consideration. It's non-idempotent physical memory attribute, and it's very different from the traditional memory type of the PMA. That means you cannot read back any value from this PMA, and just for the store, just for the AIOE two instructions. And in the end, we introduce privileged CSRs that store or contains the process ID value. And the right graph is to show you how it works. And yeah, we have the uEnqueue instructions and plus the supervisor CSR contain the process ID. And this CSR would replace the lowest bits, 32 bits of the data and send it into the target address. And it's very different from the traditional heterogeneous system architecture design, such as HSA specification, NVMe specification, what IO specification. This kind of specification focuses on the queue implementation. But AIOE is not related to that. It's no expose any queue implementation to the software. You just send out your descriptor to the AIOE. So it's more like the agent. And then when the accelerator receives the descriptor and with the help with the IO memory and the every entry contains the virtual address with the process ID, and it's called distinguish different address space. So so that's how it's work and of the AIOE. The second proposal we give out is to solve the AIOE with the virtualization scenario, okay? And we add a contribute in the hypervisor environment configuration registers to control the permission to the CSR, which contain the process ID. If a contributor is set to 0, and any access to this CSR would trap into the hypervisor, and then hypervisor have the opportunity to manage the process ID to distinguish different virtual machines. Okay, and there are some the requirements for the IOMMU design. Okay, first we need to implement a virtual IOMMU for the guest OS and let guest OS to maintain the first stage table. There are different technology pace to reach that, and I know Sci-Fi guys may do the emulated one, yeah. And but we are prefer the VirtIO IMMU implementation, so we are working on that space. It's hard to say which one is better, but I think in the future we can have a cooperation and make this progress. This is a discussion point. Second, the hypervisor should maintain the RISC tables, especially for the process director tables. But the current RISC-V I/O memory distinguish the virtual domains by the device ID, not process ID. So that cannot satisfy the AIOE requirement, and it means G-state table in device context for current RISC-V I/O memory, and we operate it to the GIDC. Here is the graph show how GIDC it is. And the gray color shows the virtual domain, and the white color is about the hypervisor domain. The virtual machine domain, that's based on the guest physical address, and that means the whole process directory belongs to one virtual machine. And because the current IOHGATP for the pointer for the G-state table is stayed in the device context. Okay, so just like those say. So how we do that? Our solution is, our proposal is the GIPC. That is very easy. That we just move the IOHGATP to the process context, and with this simple data structure modification, and we can add the GIPC supported. And with the help with the process GIPC, we can get further benefits from the performance that the process direct table is based on the physical address, and not the GPA. And that means it's no need any nested page table work. For example, 3 levels process ID directory table, and if you want to work that on the nested, you may be cost 15, 12, 9 doubles page table work. But now GIPC make the process directory based on the PA, so physical address, so no need. And second, if you have the acceleration for the middle translation entries in the TLB, and then it could save your entries in the TLB. So that's the benefit from the GIPC. And if you are implementing RISC-V I/O memory, it's very easy for you to support the GIPC, and because it's no cost for you. Yeah, it's just a simplified hardware implementation. Oh, so let's have a conclusion that we have 2 proposals mentioned. One, for the first is AIOE extension, and it's solve the overhead of the synchronization primitive for the submission jobs. Second is GIPC extension that solve the AIOE virtualization scenario. And with the help of the AIOE and the GIPC, we could explore a heterogeneous programming paradigm for the HPC to the embedded scenarios. We are seeking the opportunities, landing it to the reality, and we find one that that in the data center SIG, and thanks to the data center SIG chair, Mr. Song, that adopted the topic about how we design a HPC accelerator, and we can it's about the encryption, decryption, compression, decompression is very easy and good point for startup. The definition of the descriptor is similar to the ISA design of the instructions. It contains source address, destination address, compilation address, the length, and the OP codes and flags. But the difference from the ISA design is that the ISA source operands are based on the register composed maybe decades of the transistor, and with the fixed length of the register length. But if we move, even you move to some attached matrix extension, more scalar one, and the register may be based on the SRAM, but still fixed length. But for this heterogeneous descriptor, the source destination are that's a variable length, and you can like a procedural call to tell the device that which length you determined. And the second, the backend device could be SRAM, could be DRAM, could be persistent memory, could be remote memory, could be I/O. Is very flexible to the design. Maybe the flexible is the key problem or the gap for us to find out a paradigm programming style. It's not as a topic, but I'm very exciting. It's happened in the RISC-V community, and we can help this trade to implement. And the work result not only serve for the RISC-V, but also could serve other architectures such as the x86 Enqueue command instruction or the ARM, the ST64B V0 instructions, and all architecture could benefit from our work. Okay, final remarking, and we have sent out AIOE extension published at the Tech Privilege TG, and it have been updated to version 4, and with the help of the RISC-V communities reviewing, and very thanks to the Alan, Ved, Paul, and Greg for their review and comments, especially for the Alan. He helped a lot and gave a lot of review. And welcome more feedback from the community. And the second, GIPC has been, we have sent the pull request to the GitHub. That not means that we are rushing this to merge it. We just give out for the review and welcome the feedback. If you all contents of this presentation, we have put that in the poster, and the poster is at the west gate, and you go out and turn right. You will find it. And if you want to discuss with me with this more, and you can find me around our booth, and at a second floor is at the west side. So remember this booth sign, Xuantie, and you can find me. Okay, I finished. Thank you all patient guys for listening. Thank you.
Thank you. So, unfortunately, we don't have time for questions here, but you said where we can find you, so I'll direct all questions to Xuantie booth. Next talk is by